All right. Top 6 lessons of all time. Love this lesson. It's so cool. We're going to talk about what derivatives mean when you have more than one variable. And when we mean more than one variable, more than one independent variable. That's what we talk about with functions. So let's start real slow. When you have one independent variable and you find a derivative, if I just ask this question, you're going to know it. What's a derivative? Slope of a tangent line to a curve at a point. So in one independent variable, derivative is very unambiguous. It means the slope of a curve at a point, or rather it means the slope of the tangent line to a curve at a point. No ambiguity. That is what we define it to be. Some people get caught up like, well, isn't an approximation? Yes, but it's a very good one, and we define it to be that. That's how a derivative actually works, where it's a definition for the slope of a tangent line to a curve at a point. We define it that way. So here's the question. We're going to do a whole lot of writing about this. So like I said, I'm going to explain this for a long time, quite a bit, because doing this type of derivative is not hard, but your understanding needs to be there for you to get what it means. You shouldn't be doing this stuff if you don't understand what it means. That's what we're going to focus on. The meaning of what derivatives of multivariable functions even mean. In Calc 1, we focused on what derivatives meant, what limits actually were. You need to get it, and that will make it easier. That will make it more understandable. So let's start with this. So what in the world, if a derivative with a function of only one independent variable is a slope of the tangent line to a curve at a point, what in the world does a derivative of a multivariable function mean? Let's start with that question. So what does a derivative of a multivariable function look like? Well, let's talk about it. When I say multivariable, I mean just having more than one independent variable. Let's start with just two. So you tell me this. What is that? What does f of xy create? Let's go through the whole thing. How many independent variables do we have? Everybody, how many?
Two.
And two independent variables, it creates a 3D. There's a difference. You see, when we had vector functions, it was in one variable. It was 3D, but it was a curve. What's it mean if I have two independent variables? You plot a point, you get a height. It creates a, what's it create? Surface. That's what a multivariable function creates. It's a surface in 3D or 4D if we have more than two independent variables. It's crazy. So this is a surface in R3. I think we had the conversation earlier. R3 just means 3D, real number system with 3 axes, 3D, that's all it is. So here's the question. I'm going to actually ask the question, write it down and answer the question so you can walk yourself through the notes later, okay? So here's my first question. Is a derivative of a two-variable function, so this f of xy, is the derivative the slope of a surface at a point? Let's ask that question. I mean, it seems kind of logical, right? Because you just told me that the first derivative of a regular function with one independent variable is a slope of a curve at a point. That's all right. So is this derivative the slope of a surface at a point? What do you think? What do you think about that? Does that make sense to ask that question? Well, let's see. Bring up Mr. Happy again. Surface? Derivative should mean slope somehow, right? It should mean slope because derivative with functions means slope. Derivative of one independent variable, slope of a curve at a point. Derivative of more than one independent variable says slope of we lose it. Isn't the slope of a surface, here's my surface, at a point. You tell me. Well, let's try it. What the derivative of a function with one variable says is it's the slope of the tangent line to a curve at a point. So I want this derivative to be the slope of a tangent line to a surface at a point. So let's see. Is this tangent to that surface at a point? Yes. Absolutely. What about that one?
Yes.
What about that one? What about that one? How many tangents to this surface do we have at that point?
Infinite.
That's a bad question then. So that's a very ambiguous question. So is it the slope of the surface at a point, or the slope, I should really kind of clarify this, is it the slope of the tangent to the surface at the point? Well, that's an ambiguous question. So the answer is no, but no. Well, let's think about it. This is very ambiguous. Why is it too ambiguous? How many tangents can you put on the surface at a point? How many tangents could you do?
Infinite.
There's an infinite number of tangents. It means there's an infinite number of slopes. Too ambiguous, infinite tangents. That's the problem. That is the problem. So, yeah, we can't really do that because the question is too ambiguous. There are an infinite number of tangents to a surface at a point. So, if you understand that concept, that's the biggest issue. So, if we want to find the slope of the tangent line to a surface, which we're gonna do, we're gonna have to change the question a little bit. We're gonna have to change our approach. What if I said I want to find the slope of the tangent line to a surface at this point, but only given a certain direction? Could I do that? So if I'm headed in this direction, could you give me the tangent line? If I'm going this direction, could you give me the tangent line to that surface at a point? That's the question we're going to create. So I have a couple things I want to write down. Firstly, to find the slope of a tangent line to a surface at a point, please note this. I'm not talking about a tangent plane. That is possible. We do talk about it, but I'm not talking about that. I'm talking about... Come on, Happy. I'm talking about the line on the surface. That's what I'm talking about. I'm not talking about the plane on the surface. We do this later, okay? We will do it, but it's not now. So... To find the slope of the tangent line to a surface, the reason I'm underlining line is because I want you to know it's not a plane, not a tangent plane. We do it later, so I'm not talking about tangent plane. Find the slope of the tangent line to a surface at a point I have to give that tangent line a direction. I've got to say, I'm going to restrict it. Okay, well, what direction? What direction do I want to give it? I'm going to make a little side note here. There's a lot going on. I'll do like a 30-second, maybe 1-minute recap of all this concept in just a bit. But here's the idea. We have the ability to do directional derivatives in any direction we want. We're going to do that general idea. We're going to do it later. We're going to talk about fully directional derivatives later. For right now, we're going to... Are you listening? Some of you guys are zoning already. We're going to restrict our direction to one of two directions, along the x and along the y. And more specifically, in the x direction. I don't want you to think it's always over the x, because that's not true, but it's always in the direction of the x-axis or direction of the y-axis. Z-axis? No. Because that's not our independent variable. That's our dependent variable. That's what the surface is defined as. Does that make sense to you? Yes, no?
Yes.
Some of you guys look at me like you got dead eyes out there. Like, huh? What? You guys don't have dead eyes at the Leonard, man. It freaks me out, dude. It's crazy. It's like zombies. Don't be math zombies unless you're gonna be really good at it, and then I don't care. Just don't eat my brain. Okay, I like my brain. So anyway, to find the slope of the tangent line to a surface at a point, we gotta give the tangent line a direction. We're not gonna give it any direction, not a general direction. That's called a directional derivative. We get it later. Right now, we restrict our direction to in the x direction or in the y direction. That's the two that we're gonna talk about. Fully directional derivatives are going to come later. For now, we are going to restrict our derivatives to tangent lines along the x direction or in the y direction. How? How would we do that? How can we restrict a tangent line to a curve and say, I want you to go just in the x direction? How in the world can we do that? So let's imagine this for a second and go, okay, here's my surface. I'm hoping you can kind of see or imagine that 3D, should have got a clear one, don't have any, that 3D axis, and that's my surface. How can I make this tangent line go through that point to this surface and be in the x direction? Would it look like this? That doesn't look very good. But how would it stop me? Stop me when you think it's going to look pretty good. There. Looks like my x-axis is going this way. Well, wait a second. Is this going to be right over the x-axis? No, but it's going to be in a plane that's parallel to that plane that contains the x-axis. Does that make sense to you? So imagine that we have this, it's a horrible plane. From a plane. Didn't bring a plane today. Use my Valentine's Day stickers. They're cool. Be too busy. We'll use whoever this is. I don't know. So imagine we're like this, and we say, hey, let's take this plane that's running along the xz plane, just like that. Okay, let's move this out here until it hits that point, and then find a tangent line that's contained by that plane. Does that make sense to you? That would restrict that tangent line to being in the x direction because it's contained in a plane that's the parallel plane to something that contains the x-axis and the z-axis. That straight up and down plane that runs just like that. So if you guys feel okay with that idea, for real. That's a weird idea. Let me write it out and we'll go through it again, okay? So how do we do it? Well, to find the slope of the tangent line in the x direction, we need that tangent line to be contained in a plane that's parallel to the xz plane. I want to walk through this one more time back there. I want to walk through this one more time just to get the real feel for it. Then I'll throw out the punchline, and we'll talk about the y direction. It's going to be the same exact idea. Then we start talking about how in the world we take derivatives. I promise it's not hard, but you have to understand this next concept that we're going to talk about, okay? It's a must. All this is irrelevant if you really don't get it. You need to get it. So let's go through this just real quickly, maybe like a 1-2 minute recap, so you get the whole idea right from scratch, and then we'll blow through the rest of it. Okay, so here's the idea. With one independent variable, you have a curve. Derivatives are very unambiguous. It's the slope of the tangent line to a curve at a point. That's all it is. Now we got two independent variables. That's a surface. We're still finding the slope of the tangent line, not tangent plane, tangent line to a surface at a point. We're still doing that. But it's ambiguous. There's so many of them. So we need to restrict it because there's an infinite number of these things going on. Infinite number of tangent lines to the surface at that point. You guys get the idea. So we're going to restrict it. How are we going to restrict it? Well, we want the tangent line for now. Later on, we'll be able to find any of them. Given a different curve, we'll go right over it, okay? But right now, we're going to restrict it to along the x direction, about like that, and along the y direction, about like that. What happens with this is we go, okay, how in the world are we going to do this? How are we going to restrict it to the x direction or the y direction? The idea is, take this out here. This point is not over the x-axis, but take a plane that's parallel to that xz plane, the one that contains the x-axis. Come over here until it hits that point. If you were to do that, and you were to draw the intersection, let's make it that way. You were to draw the intersection of the plane around this surface, it's going to give you this sort of level curve. Do you guys see it? What would the intersection of a plane and this balloon look like about, roughly? It can't be a line, it's on a surface. What would it look like? Can you imagine if I took this plane and cut the balloon right here, cut it right there? What's it going to make? It's going to make an ellipse or a circle. Well, let's draw it. Do you guys get the idea of what I'm trying to do? Here's my x, y, z coordinate system. I need to find out my tangent line at that point in the x direction. That means it's got to be contained in a plane that's parallel to this one. So I'm going to take my plane out. I'm going to go, doot, 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 doot. I'm going to cut it. If I cut it, that's pretty good for me. Can you see right now, if I held it this way, you could see it even better. Can you see that plane is cutting that balloon? Hold it this way. That plane is cutting that balloon. That plane is going through that point. That plane is parallel to the XZ plane. Show of hands if you understand that concept. Now it makes the question, I love this thing. I'm going to You know, I had a teacher who actually would do that if you were sleeping. Some of you guys better be scared right now. He would come across the desk and he'd go like that. Except this one time, this kid has his fingers out. Swear he broke the thing over the kid's fingers. It's like, oh, didn't get fired. It's like, that's amazing.
Tenure.
Look what tenure does. I can do anything. I'm tenured, man. I've been tenured for 8 years. Woo! Come on, bring it. No, I'm just kidding. But the literal point is this. That was really loud, by the way. My ears are still just ringing a little bit. Sorry. Did I scare you at all? Good. I should have. Wake up. That's the point of it. The point is, if I take this surface and I restrict it to a plane that's parallel to the XZ plane. So here it is, parallel, intersecting this. This is the intersection of the plane and the surface. I go, now, find me the tangent line at that point, but only contained in that plane. This one? That one? No. That one. How now look what it does. It essentially changes a 2 independent variable system into a which one? This one. A 1 independent variable system. Because as soon as I restrict it to a plane, what I'm doing is I'm holding here's the big idea. I'm holding one variable constant. Do you guys see it? What variable? Oh man, I hope if you get, I'll be so happy. I'll be like, woo! What variable, if I'm going along the x direction, what variable am I holding constant to create this plane? Which one?
Y.
The y. The y variable. Because the y variable will be like, oh, this is like at y equals 3. Does it make sense? Y equals 3 plane comes out like that. That's what the y equals 3 plane does. It's creating that plane. And now it's saying, now on that plane and the surface create a curve. It's just a space curve. How many derivatives are there? How many slopes are there to that point on that particular curve? There is one. Because you said at the beginning of class, with one independent variable, as you're holding y constant, you only have one left. With one independent variable, there is a very unambiguous question. You can find the slope of the tangent line to the curve at the point. Do you guys understand the concept? It's a very cool concept. It says take your surface, take a plane that's parallel here, just push it out, boom, draw the intersection. That's a curve, just a curve. Now find the slope of that curve at that point. Because the plane and the point and the line are all contained in a plane parallel to the xz plane, it's in the x direction. And there's only one of them. It's not ambiguous anymore. And now if you're okay with that one. Now I'm going to write that out in just a second. And we're going to come back here and we'll talk about the y direction. It'll be very, very similar. So how do we do it? We do this. Find so that we contain the tangent line in a plane that's parallel to the xz plane. If we do that, any plane that's parallel to the xz plane is going to have y as a constant. Does that make sense? Y equals 3, y equals 5, y equals -7. I don't care what it is. But it's going to be y equals a constant. So to make this happen, you hold y as a constant. If you need a little example, I'm going to use my y equals 3. Keep in mind y equals 3. In 3 dimensions, this is a plane that's parallel to the xz plane. That's what it is. So if we hold y as a constant, this makes certain that our tangent line is in a plane that's parallel to the xz plane. In other words, it's in the x direction. Could we do the same thing for in the y direction? Could we do that? Let's try that real quick. Here's my balloon. In the y direction, what would I have to do? Come on, what would I have to do to create something in the y direction? My plane has to be parallel to what? Say it louder. Go ahead. The YZ plane. So what I would do is I'd take my plane. This is obviously not on the whiteboard. This will probably be easier for you guys to even see. So maybe the second time around, cool. The YZ plane's on the whiteboard, right? Now it's along the x-axis, so it's going to be coming out just a little bit funny. But if we bring this out and we wait and wait and wait until that plane intersects our point, basically what's happening is I'm getting this. Here's my x parallel plane. My y parallel plane would do something like, what shape is it going to create? With my balloon, what's it going to do? Huh? Some sort of balloonical ellipse? But I know that it's gonna intersect this. Anytime you intersect a plane with a surface, you get a level curve. It's why we talked about level curves. So we go, all right, it's going to do something like this. Non-Euclidean geometry that gives you a circle around any sort of sphere like that. So we go, okay, here's my x direction, here's my y direction. It's parallel to the YZ plane. Then we go, okay, in the y direction, how many tangent lines are possible if I restrict it to this plane? So it has to be in this plane. It's got to be on this curve at that point. How many tangents now? 1. 1 at that point on that curve on that surface. And that's the magic. So for the y direction, we do basically the same thing. For y direction, we have to hold the x constant. What that does is that forces our tangent line to be in a plane parallel to the YZ plane. And therefore in the y direction. So that's the idea. I'm not going to state this, but you need to make a little note of it. We don't have to worry for two independent variables about holding the z constant, because z is not an independent variable. We don't. It depends on x and y, so we don't have to worry about that. The only ones we got to worry about right now are holding x direction, holding y direction. Done. How do we do it? Create a plane, make it parallel. Boom. Creates a level curve on our surface. The points on the level curve. If you have a curve, one-dimensional idea. There's only one tangent to that one curve at that one point. Verify that for me. Y direction, same thing. Pull it out. Boom. Curve on. That's a level curve on a surface. Intersects plane. Level curve. And then we got curve, point, one tangent line to that curve at that point. That's what we are doing here with derivatives of multivariable functions. Now, we have a special name for that. Anytime, so this big idea here. Are there any questions on this? Because I want to erase this and start right from here. Any questions on this at all? Do you need another recap? Do you feel okay about it? Seriously though, I don't want to ask that and you just go yes. I want you to really know if you understand this concept. People who are missing today, or people who miss this boat, they'll be able to do partial derivatives. Guaranteed they'll be able to do them. Will they understand them? Probably not. When you get to directional derivatives, they'll be like, wait, isn't that the same thing? No, it's not. In what two directions are we limiting our movement? What two directions? X and Y. Later, we'll have fully. So, surfaces, hey, these things, right? Still a slope of tangent line? Yes, not a tangent plane, tangent line. How do we do it? Restrict it, plane in the x direction or plane in the y direction. That creates a level curve, slope of a curve. There's only one slope of a curve at a point. That's what we're doing. We're creating level curves parallel to an xz or yz plane. For real, show of hands, feel okay with it? Okay. Now this idea. I know that was a lot. I know that's a lot of talking about it. But I wanted you to truly understand this concept because it is a big deal. So the idea of treating a variable as a constant and thereby ensuring that the tangent line is in the direction of the other variable. Hold y constant, it's in the x direction. Hold x constant, it's in the y direction. That idea the idea of treating a variable as a constant and thereby ensuring that the tangent line is held in a plane of the it's parallel to the other variable, thereby it's in the direction of the other variable. That idea is called a partial derivative. Partial derivative, because you're only taking it in part of the two directions that you can move. So partial derivative. If you want to categorize some knowledge, build a schema for this stuff as an advanced organizer, partial derivatives along the x and y are a small category of directional derivatives. Sooner rather than later, we're going to talk about fully directional, so along any path. Right now we're talking about two paths, along planes parallel to x or along planes parallel to y. Then we'll have planes on any direction. We'll move between that. Show if hands feel okay with that idea. So right now, just two directions, x, y. That means parallel to the x, z plane, and y, z plane. The rest of this lesson is easy. It's honestly, it's easy. It really is. There's one huge thing. You need to know what variable you're going to hold constant. You need to know that it is going to be constant for these derivatives. And you need to know, for me, why you're doing it. You need to know why you're holding the variable constant. Because if you don't know why, you can make it through all this math and at the very end go, what am I doing? I don't know. What am I doing? It doesn't make sense. If you don't like the balloon idea, we can do this one too. If you're more of a surface type of person, and you wanted to find this, the idea is take your plane out. What it would do is create this sliver. It takes that sliver that's parallel to the xy, and then you're finding tangent to the curve at the point. That's what I tried to draw on the balloon, but if it didn't work for you, that's another interpretation. You're taking a plane, moving it out until it hits the point, make a sliver, creates a curve on the surface, but it's in the x direction. Slope of a curve at a point, done. That's what a partial derivative does. Other direction, of course, you can see it maybe. Takes a sliver in the y. That just got really kind of crazy. And then takes the derivative in the y direction. Does that make sense to you? Can you picture that right there? It kind of functioned up the graph a little bit. Did the balloon work better for you? I like the balloon a lot better because you can actually do it, but some people like this better. I want to get that off the board, man. It looks nasty to me. I don't like that. So let me give you the notation. I'll show you how to do it. I don't want to bore you completely here, so let's get some examples. So here's some notation. Hope you can tell this is one of my favorite ideas. I really love this idea. Man, I want you to love it. I want you to understand it more. I don't care if you love it, but understand it fully for sure. So for a function with two variables, let's call them x and y. When I say two variables, what type of variables are these?
Independent.
Equals z. What type of variable is that?
Dependent.
So three variables, but only two are independent. So for a variable with a function with two independent variables, here's what we do. If I want to take a partial derivative, the notation, it's like a D, but it's a curly D. You know, curly D. Yeah, like that, like curly fried. Looks like a little curly fried. So it's a curly D. That right there says partial derivative. That's what that says to you. That's what that needs to say. Partial derivative of our function with respect to x. Let's talk about what this means. Okay, check it out. This will hopefully make full sense to you now that you understand this concept. Whenever you take a derivative, always with respect to an independent variable. Always, you have to. We're taking with respect to x. That means with respect to x means we're going along the x-axis. Just like when we did f of x, f prime of x was along the x-axis. That means that x is our only variable of motion here, of movement. When you take the limit and we make these little points closer, it's along the x now. Okay? So for a partial derivative of f with respect to x, the one that we're treating as the only independent variable, what variable has to be held constant for that to work? Y. So partial of f with respect to x says that we're holding y constant. We're in this case, when we hold y constant, we're in the plane right here. That's what we're doing. It will be along the x movement. We take increment x and move it really close. That's what we're doing. So this holds y as a constant. Y constant. When I create y constant, y equals 3, what's it make for me? If I hold y equal to a number, what's it make 3D? What's it make a plane? So this is a plane. Holding y constant makes a plane. So it gives the slope of the tangent line to the surface at a point in the x direction. Holds y constant. That, my friends, ladies and gentlemen, is the entirety. When you do a partial, you're holding a variable constant. When you do a partial with respect to x, you're holding y constant. It's created a plane, level curve, tangent line. It's still a slope of the tangent line. It's still to the surface. It's still at any point, but please note, it's still at any point as long as it's on that curve. Does that make sense? That's what's happening. We're restricting it to that particular level curve. And as an x direction, we say with respect to x. That's how that's said. The y is very similar. It's just opposite. So the partial of f with respect to y, this holds x constant. Of course, that puts it in a plane. So it gives the direction or the slope. Not direction. It gives the slope of the tangent line to the surface at a point, but in the y direction. We say that's with respect to y. We're letting the y move, we're holding the x constant. That's the magic, guys. That's the magic. I really want to know if I've explained this truly well enough for you guys to grasp the concept of what we're doing. For real. Okay. Final little notation here. There's a lot of different ways that we can write this stuff. So I need you to make a small little note, and then I'll give you some examples, and we're just going to crush some derivatives. I will promise you the derivatives are not hard, but you certainly need to know what to do and when to do it. We're going to spend most of our time doing that. I'll tell you one of the biggest failings that people are going to do are doing product rules when you don't have to. That's probably one of the biggest things that people do here. So be careful on that. Are we still going to have a product rule? Yeah. Chain rule? Yeah, always. Quotient rule? Yes. But sometimes it's going to surprise you how easy these can be. Sometimes it's surprise you how hard they're going to be. We got to really watch what means what. What's held constant? What is our variable? So final note, then examples. I know I've built up the suspense, so you're all ready for it. Those two things need to mean the same thing in your head. Since f can be defined as the dependent variable z, partial of f with respect to x, partial of z with respect to x, those are identical. Also, we can make it even simpler. This is the Leibniz notation sort of idea. Remember d, dx, d, whatever, dy, dx, df, dx, that's Leibniz. The Newtonian sort of form here is that. A lot of people like that, a lot. I kind of like that one because it's a little simpler. It says you do f with a subscript of x. That is the partial derivative of f with respect to x in the x direction. It's finding the, don't forget this. What's a derivative tell you? Always, what's a derivative of function tell you? What's it tell you? Slope of a tangent line to a, I don't know, to a something. But here it's now in a certain direction, in the x direction. It's still the slope of a curve at a point, though. I just needed that to be pounded in here. Okay. Or we could do that. And that also means that, likewise with y, same stuff. I just got the chills. Did you get the chills? The first one. I really did, like for real. It's because this is a cool concept, man. You're gonna like it. All you physicsy people who probably learned this, did you understand what you were doing when you were doing it? Do you understand now what you were doing when you're finding partial derivatives? So I'm going to keep on asking you, and you got to get right every time. Wow, that's a good one for our first one. Now, I have several questions for you, firstly. What in the world is that thing? Tell me right now how many variables it has.
2.
So what's it create in 3D?
It's
It's a surface. What we're going to be doing right now is we're going to find the equation of the tangent line to that surface at any point. But we're going to do it in the x direction and the y direction. So how we start this, I'm going to do this one just straight out. I'm not going to ask for help on this one. I'm going to vary my notation. So I'm going to choose this sometimes, that sometimes, so you get used to it. Here's what the partial of f with respect to x does. It holds y as a constant. Now, that should be really cool, because from before you're like, wait a minute, aren't these two independent variables? Yeah, they are. And if you're really used to implicit differentiation, you're like, product rule, oh, it's product rule, it's got to be product rule, because you're implicit. This is not implicit any longer. These are both independent. Y does not depend on x. Y is not a function of x. Z would be the function of both x and y. Do you understand? We will talk about implicit today. But it's not this. This is not it. It says two independent variables. It's only two that are listed. Therefore, with partials, we go, okay, well, how do we do it? Just literally treat y as a constant. My favorite number is 7. I just pretend it's a 7. I literally do. Just pretend it's a 7. So I go, hey, this is 2x squared, 7 cubed. Do you need a product rule if that's a 7? Then you don't need a product rule for a partial derivative with respect to x, because that variable y is held constant. So okay, well, what do I do with that? Cover it up for a second. You're not going to change it. It's like the 2. Would you change the 2? You'd multiply by the 2, but you're not going to 2 derivatives of the 2. It's a coefficient. That's now a coefficient. So let's take the derivative. What's the derivative of x squared? So bring down the 2. We're going to have 4x. What happens with the y to the third? You leave it because it's held constant. Please listen. I know it's confusing because we say the word constant, and you go, wait, derivatives are constant or 0. They are when they're actual constant terms. But when they're held together with variables, they're called coefficients. Y acts like a coefficient here. A held constant variable, but it's connected to other independent variables. Do you guys see the difference in that? You don't just arbitrarily cross out everything because you'd have a lot of zeros. How about that one? Well, if it's partial here, I'm going to have minus. What's the first name? Well, I told you I wasn't going to, but I'm going to ask you. What's the first name?
6x.
Good. Remember, that's 2x, so 6x. What about the y? It's like 7. It's just like 7. It'd be 6x times 7. Now, of course, you can't get 42, but you think of it like a constant. It is being held constant. Can I take the derivative of that thing, 2x squared? Hey, that's a normal one, because x is our independent variable in this case. We're along the x-axis only. Y is held constant. That's 4x. Now, here's the magic question. Do you know what to do with that? Is the derivative of that 6y? Yes or no?
No.
Why not? Because it's like 7. If you plugged in 7 right there, you get 49 times 3. I don't know what that is. 47? Yeah. 147, right? Okay, cool. So if you took the derivative of 147, you'd get 0. So the derivative of this thing is 0. What's the derivative of that thing? Done. It's going to shorten up a lot of polynomials for you real fast, because derivatives of variables that are being held constant are 0. Verify that. Why is it constant?
Yes.
Verify that derivative of constant terms are 0. Notice the difference. Constant being connected to an independent variable acts like a coefficient. Constant term 0, just like the 1. Should fans be okay with that one? Okay. What's it mean? What is that? What is that? Slope of the tangent line to the surface, but only in the... This will give you the equation. This is the equation for the slope of the tangent line to this surface at any point that is in the x direction, along the plane that's parallel to the xz plane. I'm not going to write that, but that is what that's doing. It's giving you the slope of any tangent at any point, slope of the tangent line at any point, as long as that point is in the plane that's parallel to the xz plane. We call that an x direction. It's a crazy idea. Why don't you find partial of f with respect to y? Can you try that right now? I feel like I've over-talked that, and I'm sorry if I have. I get really excited about it, and I can't shut up. Too much coffee and the way that I am. My bad. If I'm taking partial of f with respect to y, what variable is being held constant? That puts the derivative in the direction of, the slope of the tangent line in the direction of what variable? So this is in the direction of the y. This way. Oh, goodness. What is it?
6y squared.
Love the 6. What next?
X squared.
Why x squared? Why isn't that 0? It's a constant held variable, but it acts like a coefficient here. So this is all one number compared to y. So it's x squared y to the
second.
Beautiful. You're doing great. Let's keep going. What's the derivative of that thing? Well, let's see. If this is 7, that's 7 squared times 3, okay, same number. But then this is a constant times y. What do I get?
3x constant. A constant.
Just 3x squared. The derivative of y is 1. That's my only variable here. Are you guys getting it? It will sink in, I promise. It will become easy for you. Right now, if you're like, oh my gosh, just wait, try a few of them, it'll get better. What's the derivative of 2x squared with respect to y?
0.
Gone. What's the derivative of 3y squared with respect to y? Beautiful. What's the derivative of 1 with respect to y? I didn't care. Yeah, perfect. This is a partial derivative. Now, what's it mean? What does this mean, everyone? What is a... Crazy.
Really surprised.
Me too. I'm having a heart attack right now. I can seriously feel my heart palpitating. I told you too much. I did a workout right before this. I'm like, yeah! Woo! Slope, man. So it's a slope of a tangent plane. Planes don't have slope. Planes have normals. Oh crap, we gotta deal with that later. Yeah, this is the slope of a tangent line to that surface in the y direction, parallel to the yz plane, x held constant. That's what we're doing. Don't let these words just roll over you. You need to understand these things that are coming out of my mouth. You understand the words that come out of my mouth? Do you? Do you?
Yes.
Let's keep going. We should have a whole bunch of practice. A whole bunch. You need to know when to use the chain rule, when to use the product rule, and for goodness sakes, when not to. Don't be doing product rule to me here. That's crazy. Okay, you're working way too hard. A lot of people do. A lot of people do. You know, I usually don't like to stand up here and just crush derivatives, but that's what we're going to do for a while, just so you get the feel of it, and then I'll start asking you more and more and more, and start doing some other stuff with it. But right now, we're basically just going to be crushing derivatives. You have learned the whole idea, okay? You seriously learned it. It's done. That's why I talked for about like 35 minutes about the idea, because now you know it. You know it. So let's find the two partial derivatives. Notice something. For however many independent variables you have, that's how many partial derivatives you can find. You can't find 3. You can only find 2. can find more than one because we have two variables. Let's find the partial of, let's find this. What's that stand for to you? Say that again, please. Partial derivative of f with respect to
X.
perfect. That's in the x direction. Slope of the tangent line in the x direction. So let's do it. True or false? If I'm doing with respect to x, and x is my independent variable, what variable is held constant?
One.
Do I need a product rule?
No.
No. What's the derivative of e dx?
X.
Cosine y. Don't do sine. Don't do that to me. Because that's cosine of a constant. It's like cosine pi. What? Well, it's not, but it is. How about that? What's e to the y? What do we treat that as? Not a product rule. What's the derivative of sine x?
Cosine.
So e to the y cosine x. Done. Done. Some of the ones that look really hard are not hard. You're going to make them hard because some of you are going to be like, I just have to do the product rule. Got him! and you're going to do it every once in a while, and it's going to happen. That's okay. But every time you do and you take the derivative, you go, wait a minute. Oh crap, y is a constant. I take the derivative of cosine y. It has to become 0 because that is a constant with respect to x. Let's do the other one. The partial with respect to y, that's what that means. Now, x is my constant when I look back up here. So I have derivative of cosine y is negative sine y, but I don't change my coefficient, and yes, that's a coefficient because x is held constant. Here, the derivative of e to the y is e to the y. I don't change my coefficient. Yes, that's a coefficient because x is held constant, so plus e to the y sine x, done. Those are my two partial derivatives, and right now you should know what they mean. I'm not going to keep reiterating it, but that's what they mean. We're going to start stepping it up a little bit. Z equals x, e to the xy squared. How many independent variables do we have? You got to kind of infer that. Well, you don't have to infer it. It's listed. How many independent variables do we have?
Two.
What are they? What's z?
Dependent.
Okay, so let's find the two partials here. Let's first find the partial with respect to x. Everyone in class right now, if I find the partial with respect to x, what's my independent variable? No, independent variable.
X.
What's being held constant?
Y.
Perfect. So if I do with respect to x, oh, do you see it? Do you see the shift in what we had before and what we have now? What's the problem here? Now you have a function of x times a function that has x in it. That is when you use the product rule and no other time. This is for sure product rule. Can you please set up product rule for me? Be careful when you do the ddx's to use the curlies. Okay, you got to use curly dx. If you need to see that, you're like, curly, what do you do? Don't do this. This is not what we're doing. We're not doing a straight up derivative. We're taking a derivative in a certain direction, and our notation for that is a partial. So we do derivative of the first with respect to x times the second plus the first times the partial derivative. I do it all the time. I release it every time. With respect to x of the second. Derivative of the first times the second plus the first times the derivative of the second. Of course, we mean partial derivatives. Show of hands if you feel okay with that so far. Yes, no? Guys over here on the left? I want to make sure you're all with me. I don't want to leave you behind on this lesson, okay? Let's start it. What's the derivative, right-sider's derivative of x with respect to x? What is it?
1.
Perfect. The partial, that's 1. Do I have to take the derivative here?
No.
So I have e y squared plus, do I take the derivative here?
No.
Follow the ddx's. That's just going to be x. Now, oh goodness, do you remember how to take derivatives of compositions? Uh-huh. And do you remember how to take derivatives of exponentials? So we're kind of reviewing. I'm teaching you as I'm teaching you here. What's the derivative of this thing, please?
Y squared. E to that.
Okay, so we're going to get exponential back. You never, by the way, if you've never heard this before, you never, ever, ever take two derivatives at once. You always take a derivative of one function and then something else, just like product rule. You don't take the derivative at the same time. One derivative is here, the other one's here. One derivative is the derivative of the function, and then later we take the derivative of the inside of that function. It's never done at the same time. I know you write it at the same time, but you never ever do a derivative of a function and put the derivative inside. That never happens. It's always later, always done separately. Feel good with that one? Next question. Everyone right now should have this down. Do I need a product rule right there?
No.
Explain to me why not.
Y squared is constant.
Okay, so what's our derivative?
Y squared.
Beautiful, you guys are doing great. Now, can you clean it up just a little bit? We can do things like factor, all the stuff that you know about. So the partial of z with respect to x is e to the xy squared times 1 plus xy squared, done. You're going to get a little bit lost in what you're doing and forget what you're doing. This is a derivative. That means it's a slope of the tangent line to a surface along the x direction. That's what we're talking about. For real, are you okay? Do you think the partial with respect to y is going to be easier or harder? How about this question? Does the partial with respect to y involve a product rule right off the bat? No, it's like 7. It's like a number 7. So the partial here goes, okay, let's take the derivative of this thing. Derivatives of this thing gives you exponentials back, then takes a partial with respect to y of the inside of that. That's like 7, man. You just hold it right down there. It's just a constant. Derivative of this is this times the derivative inside. Derivative of the function times derivative of the inside of the function. Now you help me with that. Right setters only, you guys. Can you tell me the derivative of xy squared with respect to y? Notice you have to put that notation. It tells you what to do. Follow the ddx. Don't do a lot of it in your head, okay? For now, write out a lot of stuff. It's very easy to start doing things wrong when you're not writing stuff down. So far, I've let you do a lot in your head. Now we kind of stop that, back off a little bit, take your time here. In this case, it's a lot better to get the right answer slowly than the wrong answer quickly, because you're going to mess stuff up a lot. If you try to do all of it in your head, it gets ridiculous. What's the derivative of that with respect to y, please?
2y.
Beautiful. Let's combine this stuff. Let's find the slope of the tangent line to this surface, but in the y direction. So fans are okay with that one. Can I mess with your heads a little bit? Can I just ruin your minds for just a second? Yeah? Oh, before we take a break. Yeah, this will be good right before we take a break. Just ruin your heads. Yeah, I love this one. Love this stuff. What's going to happen is we're going to do this one. I'm going to give you one to do on your own during the break. I'll give you a couple extra minutes. I want you to actually try it. I don't want to record while you're just working, okay? But I want you to try. I'll give you like two extra minutes to do that. But I want to talk about this one first because this one throws a lot of people for a loop. Like, we can't do that. That's crazy hard. Let's try to start with the derivative of z with respect to x. Ladies and gentlemen, if I do that, what is my independent variable? There can be only one. There can be only one. What is it? And what's my constant? Good. If y is a constant, can I take that derivative?
Yeah.
Trust me, think of these things as constants. For real, it will help you. If you do that, you go, okay, well, what's the derivative of z with respect to x? Well, that's an exponential. With exponentials, we get exponentials back times the natural log of that exponential. Do you recall that? You literally do the same thing with e. I promise you do. Watch. If that's an e, what's the derivative of x? You know that one.
EDX.
ln of e. Oh, but wait, ln of e is 1. That's why we get that magic little rule out of that. It's a gorgeous piece of work. So if that's a constant, we go, oh, we get the constant back, but then we multiply by the natural log of whatever that constant is. That's the derivative. Pretty cool, right? Now, how about the derivative of z with respect to y? How about that one? What is our independent variable now? You should always ask these questions before you start. Get the variable in your head, get the constant in your head. You do not just rush in and start doing this stuff. You get it in your head. What's the independent variable here?
Y.
Good. What's the constant?
X.
Okay. So if I had z equals, you said y to the 7th, could you take that derivative?
Yes.
With y being the variable? Absolutely. What do you do with the 7? And what do you do with the exponent?
Subtract.
If that's a constant for y being the variable, x is held constant, we get bring down the constant exponent. Put your only variable, subtract 1 from the exponent, done. That's the derivative. You really need to get in your head that these variables can be held as constants. That's interesting stuff right there. I love that one. Does that make sense to you? Now I'm going to give you the one I want you to try. Be very careful on it. Use product rule when you have to. Use quotient rule if you have to. Don't use it if you don't have to. Here's the example. I got to warn you, when we come back, I'm going to do this one very quickly, so I'm not going to be showing a whole lot of work. That's your job. You got to show the work on this. X squared cosine, wait, h? What the h is that? Do you remember? Gosh. Oh my gosh, are you kidding me? Try that one. Okay, so you should have had time to at least attempt this thing. We're going to find the partial derivatives with respect to the two independent variables that we have. Like I said, I'm going to cheat a little bit and not show you every single step. So do as I say, not as I do. But let's think through this first. If I want the partial of g with respect to x, what's my independent variable? Always think through that. What's my independent variable?
X.
What's being held constant?
Y.
Good. Every other variable. So in this case, y is only the one. Do I need a product rule here? Yes or no?
Yes.
Yes or no? Everybody, yes or no? So product rule says derivative of the first times the second plus the first times the derivative of the second. Now, the derivative of the second, derivative of that thing. Yeah, you might have to look up what the derivative of cosh is. It's sinh. It's not negative. So it's sinh. Chain rule says never ever take two derivatives at the same time. You always take the inside one later. Now the derivative of this, let's look at the derivative of the inside of that function. What's the derivative of x over y when x is my variable and y is held constant? What is it?
1 over y.
1 over y. That's it. I need to show of hands if you got that. That's wonderful. Well done. So we might want to clean it up just a little bit. I'd move the 1 over y here. Don't touch that. That's an argument of an angle. But that's about it. That's about all I would want you to do. Maybe factor out the x if you really felt ambitious. I don't know. That's about as good as you got. You guys with me on what I'm talking about for that one? Now, for the next one, partial derivative of g with respect to y. What is my independent variable here?
What?
What's my constant?
X.
Do I need a product rule for the derivative with respect to y? No, because it's like 7. That's just a number. So when I do this, we go, okay, the derivative of this, that's a number. It's just really here. This is the only function that has a variable in it right now. The only function that has a y, our independent variable. So we have x squared. Do I still get sinh, yeah or no?
Yes.
You still get sinh. You still got to take the derivative of the composed upon function. So derivative of the outside function, leave the inside alone, times the derivative of the inside. Oh, goodness. What is the derivative? Shoot. Of this with respect to y?
Negative x over y squared.
Good, yeah, because we bring this up, you'd have x, y to the negative 1, that's a constant. Negative x, y to the negative 2, bring it back down. Better be put in parentheses here so it doesn't look like a minus. And then, yeah, clean this one up just like we should be cleaning this up. Move the x squared over y here. That's about as good as we can make it. That is about it. Listen, I really want to make sure that you understand this concept before we go any further. Why we did use the product rule for x and why we didn't for y. And if you got that, you understand that chain rule idea that we just did, you're going to be fine. Show of hands if you feel like you're going to be fine. Good, okay. Let's move on. Like how I changed that right when you raise your hand. It's like you're going to just be fine on everything for the rest of your life. You're good. Just no worries. You got Calc 3 now. What? Cool. All problem solved. The same thing holds true for functions with more than two, for functions of however many independent variables you got. So we're going to do just a couple, flying through them real quick. Keep in mind, though, it doesn't mean the same thing. It means this is a weird concept because that's got 1, 2, 3 independent variables. 1 dependent, but 3 independent. That's a surface in what dimension? So this will create a plane sort of idea in 4D along the whatever axis I choose, x, y, or z. Now that z is an independent variable, I can find the partial with respect to z. Do you guys get what I'm talking about? So this is going to create for us a curve along this surface in 4D and find the equation for the slope of the tangent line to that surface in 4D, but only along the direction of one of these axes. That's what we're doing. The concept extends. So let's try it together. Let's find partial of w with respect to x. We're going to right and left, back and forth. So right-siders, can you tell me the derivative of this first term with respect to x, please, quickly? Plus, middle people, I want you guys, middle people, tell me the derivative of this term with respect to x, please. Beautiful. Left-siders, derivative of this term with respect to x. Why? Why 0? That's a constant. What's the derivative of this with respect to x? 0. So if x is our only independent variable, the rest of them are held constants, like 7 and 8. I don't care what you use, but just make sure that you understand they're constants. How about partial of w with respect to y? Let's start over here. First term. Middle people. Right side people. Come on, don't leave me hanging. Everybody.
0.
Why? No whys. Can I do partial with respect to z? Before we haven't been able to do it, can I do it now?
Yes.
Now that z is an independent variable, that's absolutely correct. You can. So how about this one, whole class, derivative of this with respect to z?
0.
Derivative of this with respect to z?
0.
How about this one?
2
How about this one?
-2.
Are you getting the hang of it? Is it super hard? Do you understand what we're doing, though? What's a derivative? Of functions, it's a slope of a curve at a point. Just of over a surface along parallel to a plane or axis. That's what we're talking about. So this next one, we go, okay, I want to just talk about 2 of them. I want to talk about this one first. You're going to like this one. Can you find the partial derivative of f with respect to x? What's my variable here? Think it through. Come on, what's my variable here? Everything else is a constant. So, for this, do I need a quotient rule for the derivative of f with respect to x? No. This is fantastic. What's the whole derivative then? If this is what's the derivative of x?
1.
Times a constant would be w squared over. That's just a fraction, folks. It's a big 7. Just think of it as a big old 7. Just a constant. Yes, no? How about this one? Do I need a quotient rule to deal with that derivative? Can you please set it up for me? Do you remember quotient rule? You remember the rhyme for it? Low D high minus high D low, square the bottom and away you're done. That rhymes, right? No? Oh, and away you go. Low D high minus high D low, square the bottom, away you go. It still works. It still works. Just be careful on what's your variable. The only variable we have here is W. So low D high minus I ran it. Shoot. Low D high minus high D low. Well, now D low. D low is the partial derivative of this with respect to what? W. With respect to W is what I'm talking about. It's this guy. It's that guy. That's what I want. What is that derivative there? What's the derivative of Y with respect to W?
0.
Do I need a chain rule here? It's kind of a stupid question. You always need a chain rule for everything you're doing in life. Ever. Like forever. So this would be 0, but cosine ZW times the derivative of ZW with respect to W. Goodness. What's the derivative of ZW with respect to W?
Z.
So this gave us this. That gave us just Z. I don't want to lose you here. We spent too much time for me to lose you here. Do you guys see at least the quotient rule at work? That was like one. I'm glad one of you has seen the quotient rule at work. Do you guys see the quotient rule at work? To understand how to get low D high, and we get this 2xW. Yes, no. Then we got high D low. This I would write it out. I don't want to do a lot of this in my head. I'm going to write this out at least like this. The derivative of this junk with respect to W is 0. Chain rule says cosine, leave the inside alone. Derivative of the outside times derivative of the inside with respect to the same variable. Derivative of ZW is like derivative of 7W. It's 7. It's Z in this case. Then if we clean it up just a little bit, man, okay, we got a Z, we got a cosine ZW, and we got this stuff out here. Could you factor? Yeah, you could factor some stuff. If you can simplify some stuff. I'll ask you one question. Can you simplify this with this? Yeah.
No.
If you do, you're going to make me cry. Please don't make me cry. It breaks my heart just a little bit every time. Only if you could factor could you simplify that. Right now, you're basically done. I know you're all scribbling furiously down. I know some of you guys look like you're having a tough time with this. If you are, can you ask me some questions right now? I promise I can answer them.
Sure. Ask me anything you want.
I need to know if you follow that. That's what I need.
No.
What part?
Some parts. No.
Okay.
It's
So,
just some parts.
do you get the low D high minus high D low square the bottom whole thing? Do you know why we have no Y left? Do you know why we get cosine?
Yes.
Do you know why we left that alone?
Yes.
Do you know why we got a Z here and not a W? And not a 0? If we would have got a 0 there, you wouldn't have had to do that chain rule. It would have been a constant. It would have been 0 the whole thing. Make sense? Organize your terms. Factor if you can. You're practically done.
And it's kind of like one of those things where like you just have to look at it for a while. Like, yeah,
Sometimes. Yeah, sometimes you do. Can I throw in like a mind grenade just a little bit here?
I thought you already threw it.
Oh no, there's another one. Do you really feel okay with the idea?
Yep.
We've spent a very long time on the idea behind it. Now we're trying to accomplish the task of doing derivatives. There's one more thing we have to do. Just like in section 2.7 of Calc 1, when you do implicit derivatives, we can do them here too. But there's a major difference to our implicit derivatives. When we did implicit derivatives before, x was always the independent variable and y was always the dependent variable. Does that make sense? Well, how many independent variables do I have now? So usually 2. Here we have several more, but let's start with 2, okay? Then what's my dependent variable now? Z. So there's a difference in our implicit differentiation. We can still do it, but z is the variable defined to be implicit, the implicitly defined variable, not y. So let's work on that. Let's just jump right into it and see what we're going to get. So if I'm looking for partial derivatives, you know how implicit works, right? We do a derivative of both sides with respect to, it's usually x. But now it's with respect to just one of our independent variables. What do we have? So we're going to be looking for the partial of z with respect to x or with respect to y. So there's 2 ways to go about it, and you got to do both of them. So we can find partial derivative of z with respect to x or with respect to y implicitly, just like we can find them here as well. Let's start with this problem, a simple one. I'll give you one that's a little more tasking. We'll do just maybe the first step here. Then we'll talk about something that's not any harder, just continue this idea. You know, my first question to you is, can you recognize that this is implicitly defined? Can you recognize it? Explicitly defined functions have one variable equals, you never see this variable again, ever. So if it's w, you never see w's. It's all other stuff. If it's y, you never see y. If it's z, you never see z. If you have something that goes, oh, here's x, y, z equals 8, 8's not a variable. That's crazy. That means that we're going to imply that one of these variables is defined by the other variables that are there. In this case, we're going to assume that z is the implicitly defined variable. So z is this function of x and y, like we normally define it, that we don't know. It's magic. It's just some hidden function in there. It's implicitly defined. So what that means is that there's a couple things we got to remember about implicit differentiation. First, when you take a derivative, do you take it on one side or both sides?
Both sides.
Please remember that. Take a derivative on both sides. You have to do that. So recall this. Derivatives happen on both sides. Also, when we did implicit derivatives before, like in Calc 1, anytime you touched a function of x times another function of x, you needed what rule? By multiplication, what rule did you need? Okay, if you had this. That's an implicitly defined function on y. So y is the implicitly defined variable. What would you need to do that derivative? Would you need a product rule?
Yes.
If we have one independent variable x and y is the dependent, you go, oh yeah, x is a function of x and y is some function with x's in there somewhere. It's a function of x times a function of x. That's what we're talking about. That's why we had to have the product rule from implicit. If you don't remember implicit at all, man, probably go back and watch that video at some point. To like, how do you actually do implicit differentiation? That's section 2.7, all right? The idea is, if you have a function of x times a function of x, you needed a product rule. If you had a function of w over a function of w, you needed a quotient rule. Now that we have this thing, you go, oh, I've got a function of x, function of y, both independent, but I have a function of x times a function that has x's and y's in it. This is a function of x times a function of x because z is implicitly defined. Does that make sense to you? Z is now the implicitly defined variable. So z is a function of x and y, which means this. I'll make it very clear if that makes no sense. You're like, oh my gosh. First, watch 2.7. Second, because now z is our implicitly defined variable. Second, to make it just simple for you, if you ever have x times z or y times z, product rule. Every time. Does that make sense? X times y? No, they're both independent. But x times z, y times z, any independent variable times a dependent variable, you need a product rule. So let's start with this. I want to find the partial of z with respect to x. We'll do with respect to y in just a second. Let's walk through it real carefully. Everybody, how do you start implicit differentiation? You take with respect to, in this case, x. Let's show that. Let's do a partial with respect to x of one side. Equals partial with respect to x of the other side. Okay, everyone in class right now, what's the partial derivative of 8 with respect to x? What is it? Good, constant, still works. On the left-hand side, look at the board here with me real quick, please. What are my two independent variables? Quickly, what are they? X and independent. X and y. Do I need a product rule? No, because x is the variable, y is not. Does that make sense to you? It's weird. It's going to flip your head around a little bit. So when I take the derivative of this with respect to x and y are both independent. So when I say with respect to x, y is held to be constant. All the other independent variables are constant. That's what we're doing. So here we go. Okay, this guy right here, this is 2x with that y, because y is held to be that constant, just like a coefficient, just like 7. Can you guys get that one? This is no different from anything else we've done. This one's going to be different. Here's why. Here's why. That's product, yeah? And z is some function that has x's. Maybe it's x squared minus 1. I don't know what it is. Maybe it's x squared minus y. I don't know what it is, but the point is, there's an x there, and there are x's in there. There's x's in there. Does that make sense to you? Which means if I have x times a function of x, you need a product rule. Are you clear on that concept? So the product rule says derivative of the first. I'm going to write this one out for you. Times the second plus the first times the derivative of the second. This right here is the derivative of that little teeny piece. Derivative of the first times the second, I just don't know what that is, so I leave it z. Derivative of the first times the derivative of the second, I just don't know what that is, so I leave it z. For real, are you okay with that one? For real. Taking a derivative. Partial derivative. Now, for sure? See the product rule at work. Next question. Oh man, if you get this, I know you got it. If you don't, we do a little bit more work. Does this derivative need a product rule when I'm taking a derivative with respect to x?
No.
Why?
Y is constant.
Exactly. Y is a constant. Is that... Wait, how about this? Is this whole derivative 0?
No.
You get it. If this is a function of x in there, you have to take the derivative of that. Does that make sense? And we know this, so every time we take derivatives, I kind of messed that up. Every time we take derivatives, we go, okay, well, here's 2yz. Here's the y. Bring down the 2y. Here we take the derivative of z. It's z to the first power. But then, because it's implicit, you always have the chain rule. Then we take a derivative of the inside with respect to x. Honestly, if you're struggling on implicit, watch 2.7. It will clear everything up. And then this becomes pretty easy. You just have to switch your head to what we do with y's, we now do with z's. Are you clear on what I'm talking about? Okay. Equals 0. This one's done 2xy plus, hey, everyone in class, what's the derivative of x with respect to x? So we get z. Plus no derivative here. What's the, now here's the question. Look, this is what's important. What's the derivative of z with respect to x? The derivative of z with respect to x. That's why it's implicitly defined. You can't tell me what it is, because you don't know what z actually is in terms of x and y. We just go, oh, we need a dz dx, or partial z with respect to x. You remember how every time you touch a y with a derivative, you get a dy dx? Now every time you touch a z with a derivative, you get a dz dx. Or dz dy, depends on what we're doing. Plus 2y times z times another dz dx. I know I'm saying d, it's actually partial, but that's the idea. Partial, no, man, they're both inexplicitly defined. Okay, you don't need that. They are independent. That depends on x, partial. That is also depending on x. Not partial, but you definitely have a dz dx. So fancy feel okay, for real. Now, do you remember what to do with that?
Yes.
Move what?
Solve for dz dx.
Solve for dz dx, or partial of z with respect to x. So I'm going to keep this one and this guy, subtract those, or subtract these and keep these. It does not matter. You know what? We're going to be fancy because I'm running out of time. I don't want to waste time doing algebra. I'm going to keep these. I'm also going to factor. I'm going to subtract this. And then we're going to divide. I could use a double check, but I'm pretty sure that's right. My next question is, even though you really, really want to, because I want to, man, I love crossing stuff out. Can I cross any of that stuff out? Don't do it. MC Hammer, man. Can't touch this. No? Can't touch this. Hammer time. Used to love that stuff. Try the other one. Right now, try the other one. Do the partial of z with respect to y. We can do it over here. Oh man, now I got vanilla ice in my head. I don't know why I made that jump. That was a bad jump to make. Partial derivatives, derivatives in general, implicit derivatives, always start with derivatives on both sides. Don't care what you're doing. Always starts on both sides. Partial derivatives, any derivative whatsoever of constants is always 0. Partial derivatives with respect to y says y is our only variable, x is held constant, z, it's a dependent variable. It has y's in it. So we go, okay, hey, derivative of this with respect to y, we get x squared. Do you see why we get x squared? Derivative of y is 1, done. Derivative here, I do not need a product rule. This is like a 7, so I'm going to keep my x. Derivative of z is 1, but I have a partial of z with respect to y. If you got that, I believe that you know what you're doing. Did you get that? For real? Derivative of x? No, don't do that. That's it's like 7. The derivative of 7z would be 7, but then we touched a z with a derivative. You need partial of z with respect to whatever you take the derivative with respect to. Y in this case. Do you get it? It's kind of cool. Do I need a product rule here? Everyone in class, do I need a product rule there?
Yep.
Derivative of the first times the second plus the first times the derivative of the second. Derivative of the first says derivative of y is 1, z squared. Plus the first times derivative of the second, that's 2z. Chain rule gives us a dz, dy, partial z with respect to y. If we can collect our dz's, and we subtract the only terms, and we factor, and we divide. I think, to make sure, yeah, that's right. I'm not going to hold your hand on algebra. I can't do it unless I made a mistake. Then I guess I'm going to have to use my words. But can you double check me to make sure you get the same thing I got? Have I killed your brain so far or something? Yeah, a little bit. Do you guys want to do another one just to make sure you got it?
Yeah. Yes.
We're going to do just the first step on this. We're not going to solve for the partial derivative itself. I just want to get the feel. I just want to make sure you get the feel for it, okay? Just the feel. Firstly, can you tell that that is implicitly defined? If it's not equal to a variable that you don't see in there, it's implicitly defined. So we go, yeah, that's implicit. In terms of what variable? We're going to assume it's the z. So z is in terms of x and y. Are you clear what I'm talking about? So let's go through it. If I was to do the partial derivative of z with respect to x, if I was going to do that, first thing I'm going to do is take a derivative on both sides. Yes, no? So I'm not going to show that, but let's go through it. If I take a derivative on both sides, what's the derivative of 0? What's the derivative of 1? What's the over here? What's the derivative of this guy? Since this has x as my independent variable, y is being held constant. Can you tell me the derivative of this guy? What is it?
2y.
2. I'll take the 2. 2 what?
1.
Oh goodness, I've lost you. You can tell me. Look in your face.
Negative 2 sine.
So it should be negative 4y sine x.
Let's talk about that. Can you please tell me what my variable is here? There's kind of two answers. My independent variable is what?
X.
What's my dependent variable?
Or z.
Z. Let's get that straight. Let's ask it again. What's my independent variable right now? What's my independent variable?
X.
What's my dependent variable?
Z.
Z. What's y?
Constant.
Good. So when I'm taking derivatives here, I'm looking for x's and z's. Y's are held constant. You guys get it? Let's do this then. This is 2 what's the derivative of 2 freaking cosine x? What is that?
Negative 2 sine.
Negative 2 sine x. So that means the derivative of this guy is negative 2 sine x, but then times the derivative of the inside of that. Chain rule! Come on, chain rule this thing for me. What's the derivative of x plus 2y with respect to x? What is it?
1.
Beautiful. Do you guys get where the one's coming from?
Yeah.
Are you sure? Right-siders, yes, no. I'm not getting a whole lot from you today. Are you okay?
That's constant.
Question. Is the derivative of this whole thing 0 Because it doesn't have any x's in it, is it?
No.
No.
Come on, help me out. Come on, you can't be silent the whole time. You can't be silent. Does this go to 0?
No.
No.
Why not?
Z's.
Z's do have x's. They're in there. They're in there somewhere. So when we take the derivative, hey, what's the derivative of sine of x? What's the derivative of sine?
Cosine.
So this would be cosine of crap times the derivative, well, let's do it this way. The derivative of the crap. If I take the derivative of this, that's going to equal 0. What's the derivative of this with respect to x? Notice y is like a 7. Y is a constant. What's the derivative of this? Well, z would be the variable. It's implicitly defined though. So the derivative of this would be y. Derivative of the z is, but then we have a dz dx. Do you see where the dz dx is coming from? Partial z with respect to x. Are you sure? Hello, yes, no. Yeah?
Yes.
Okay. I'm going to leave it there. What you would do next is you would just basically subtract this and divide, and you're done. But I'm going to leave it right there. I want to try this one. I have to move quicker. I don't have time to really just do any more. I think I've done a lot of examples today. Eric?
The product rule for the initial size. Only to the product rule is with respect to the variable, to the independent variable that you're taking the partial.
Absolutely. Yeah, if that's my variable, that's a product rule. If that's my variable, that ain't. Which begs the question, if I do partial z with respect to y, I did not have a product rule here because this right here is not this independent variable. It does not match up. Am I going to have a product rule for this with that?
Yes.
Yes.
Okay, I'm going to give you the answer. I'm going to do it right now in my head. When you get home tonight, you need to work on this. You need to make sure that you can get the same thing I'm getting right here. So the derivative with respect to y of this thing is derivative of cosine is negative sine. Here's the keep the inside the same. The derivative of this with respect to y is 2. 2 times 2 gives you the 4. Do you see where the negative 4 sine of that bunch of junk is coming from? If you do, then you're getting it. Plus, derivative of this guy says, okay, cosine, keep the inside the same. But when I do the derivative of the inside, that's now a product rule. Derivative of the first times the second plus the first times the derivative of the second. Did you catch it? Derivative is cosine, keep it the same. Derivative inside is, oh my gosh, that's a product where it has my variable times something that's got my variable in it. That's a product rule. Derivative of the first, that's just z, plus the first times derivative of the second, that's dz dy. That's it. Now there's a glaring error on the board. It's something that happens all the time. People do it. It drives me absolutely crazy. What's missing? Is it? Yes. Do you guys see the parentheses missing? Yes. This has to be there. Has to be. It's a product rule being multiplied by something. You've got to have that. It's a big deal because if you solve for it, dz, it'd be a lot different. Partial z. Okay, I think I've gone a little bit as far as I want to go with these single partial derivatives. Show of hands feel okay with it. Now, we're almost done. I have just one more example before we're going to stop for a little bit. Then we're going to come back and finish this up with some more interesting stuff. We'll do a word problem that shows you how this relates. I really want to make sure you understand this can be used for real stuff. It's not just abstract garbage, all right? So I'm going to do at least one of those. I'm also going to show you something really, really cool when we get back. Before that, though, I have to make sure you all at least see this stuff before we take our break. You may not leave without seeing this. It is important. Here it is. What do we just spend like our lives just doing? What was it?
Derivatives.
What type of derivative?
Partial.
Partial. What type of partial? Implicit, and then we just regular old partials. What degree of derivative did we just take? First. Are there more?
Yeah.
Woo! There are higher derivatives. No. Please. Please, no. I'm begging you. Please. We're going to. We're gonna do it. We're gonna go there. Let's start with 2. Okay, you know what? Put it in the middle. Put it in the middle of your paper. Like, leave a section. Put it here. We're gonna make a nice little tree out of this. What can we do? What can we do? Hey, with 2 independent variables which we have, how many partial derivatives can we take? 2. We can take a partial derivative for every independent variable that we have. Does that make sense? So we can do 2. We could do partial with respect to x, or partial of f with respect to y. We could do that. Here's the issue with higher derivatives. It's not that much harder. It's actually sometimes easier. Because I get to give you easier problems, otherwise the derivatives could just get out of hand. I can give you those too. I probably won't give you that many of them. Because you have more independent variables, you have more paths you can take. You see, with one independent variable, a second derivative goes, just continue with your x's. Hello. You just take another derivative. And take a third derivative. Just continue with your x's. But here's the deal. What if I took a partial derivative with respect to x? Is there still x's and y's in that derivative? Yes. So I have a choice to make now. I could continue and do a partial derivative of f with respect to x twice. A second partial with respect to x both times. But I could also do this. I could take a second partial derivative of f, but I could take it with respect to x the first time and y the second time. What if I wanted to switch? Go, hey, let's do x first, then y. Please note this. Please make a note of this. This, I'm not writing this incorrectly. This is taking a partial derivative of f with respect to x the first time and y the second. Why the difference? Because when you take derivatives and you take another derivative with respect to y of something you already took a derivative, it's backwards. That's why. And when you put it together, the x came first. You're taking a derivative of something you took a derivative with respect to x. Do you guys see the scenario there? It's backwards. This says x first, then y. If you want the notation for it, here's the notation. You could do that. Partial of x of f with respect to x 2 times in a row. Or you could do that. This one, man, I hope you guys are awake enough to notice this, all right? I like this notation a lot better than I like this, and here's why I like it. It's going to be hard for you first to get used to it, but here's why I like it. This tells you the order exactly from left to right. But notice the switch. Please note the switch. This is partial of f with respect to x, then y. This is partial of f with respect to x and then y. They mean the same thing, but notice how they're a little switcheroo. I showed you why this one is the way it is. This is a little bit nicer because it tells you in order. You guys get me on that one? Same thing here. You got z, x, y. Well, the same thing happens here. We do partial f with respect to y, but you keep going with that. We can do a second partial with respect to y twice, or we can switch it up. Second partial with respect to y, and then x. We can write this as fyy, fyy, zyy, Or this one? Oh man, you tell me. Would this be xy or yx? What would that be?
Yx.
Good. I do want you to know, I'm not going to draw the tree for you, but the same thing works with other, like more independent variables. You can 3, 4, whatever you want. You keep on going with this tree. Tell you what I'm going to do. I'm going to start off with a really easy example because I want this to be fully understandable for you. Do they get rougher? Yeah, the derivatives get rougher, but I don't want to crush your spirits by just doing hardcore. I've done some hard derivatives today. You've noticed them, right? We've done some pretty hard ones. I'm not the type of teacher to give you all easy stuff all the time. I'm going to give you something really easy now, just so you see something really cool. Man, I can't even talk anymore. Some water. So you see something really cool. Ready for it? We'll do 2, then we'll take our break. We'll come back and knock this thing out of the park. We are going to move so fast through this because right now at this point you should be really good at doing at least the first partial derivative of a polynomial sort of thing like this. So left-siders, come on quickly. What's the derivative of this with respect to x, please?
3x squared.
Love it. Keep on going.
Plus y plus y cubed.
Uh-huh.
2 minus 2. 0.
0, because x is our only variable here. Show of hands, feel okay with that one. Perfect. Let's do this. Let's take our second. With respect to x twice. That's how we write that. Second derivative of g with respect to x both times. Basically, just keep on going. Treat x as your variable. Let's keep on going. Left-siders only. Tell me what this derivative is, please.
6x y squared.
What about the rest of it?
Gone.
Okay, now let's do one more. And I want left side for all of this stuff, and the right side you get your chance in the next one. Can we also do the second derivative with respect to x and then y? Notice, this says take it x and then take it y. Let's try that one. Left-siders, you get this one as well. Notice how we're doing a switcheroo. We took the derivative with respect to x. Now I'm saying now switch. Now x is constant. Now let's think about this function, but with y as our variable. Left side, come on. Lay it on me. What do we got?
2y 3x squared.
So 6 x or x squared?
X squared.
You got it.
Y.
Because y is now my independent variable. Do you guys see the switch? Are you sure you see it? Some people don't. Here, x is our variable. We go, okay, 3x squared, leave it alone. X gone, we just derivative 1, y to the third. Here, negative 2, cool. Now, if we do that again, x is still our variable. We'd have 6x, y squared. Everything else is gone. No x's. If from here, I do a partial with respect to y. So think of y as my variable now. Here, think of y. That's 6x squared y. That's 3y squared. That's still 0. Does that make sense? That's what's happening. Right side is your chance. You tell me. Come on, quickly. Let's go. Partial of g with respect to y. Let's go. Okay, this is awesome. You're making me feel real confident about your skills. Come on, people. You are the right side. Now that we have that definition, let's see. That's axiomatical. So you are the right side. Let's keep on going with this this idea. Take the derivative of g with respect to y. I need to know that you can do it before we move on. What is it? X cubed
plus 3y squared.
3 Beautiful, like it's somebody else over there. What's the derivative of this with respect to y? Come on. Somebody else over there. What's the derivative of this with respect to y? What is it?
3.
Huh? 3. Beautiful. Let's do the second partial of g with respect to y both times. So you keep on the same vein. So this derivative of this now, second derivative, but with respect to y. Come on, right-siders. I want more than just two people over there giving me answers. What's the derivative of this with respect to y, please?
2x cubed.
And the derivative of this is?
6xy.
And this?
0.
Beautiful. Now let's drop it down, and let's take the second derivative of g with respect to x after having taken the respect to y. So this says you took the derivative with respect to y. That's this. But now you switch the idea of the independent variable, and you go, okay, now let's do that one. So now, what is my independent variable here if I'm trying to accomplish this? What is it? Everybody shout it out. What is it?
X.
It is x. What's the derivative of this? Let's look the same. What's the derivative? What is the derivative of this thing that I've already done with respect to x? That's what that means. Okay? With respect to x. Come on, right-siders, it's your chance. Your time to shine, man. What is it?
6x squared. That's 3y squared.
Beautiful. I don't want anybody to ask me any questions right now. I want you to do one more. We'll stop after this for our break. Trust me, you want to see it. It's worth it. It's worth it. I want only two things. I want f of xy, and not f partial derivative f x then y, and I want partial derivative f y then x. I want those two things. That's what I want. Kind of like that notation a little bit better, don't you? Tells you, well, I do at least. Tells you exactly what to do. Finally. Now, I'd be so happy if you guys get. I'd be so happy if you get this. It would just make my heart just flutter with good feelings.
Yeah, that's just heart palpitation.
Is that what that is?
Yeah, too much coffee.
Too much caffeine. Happens to me when I'm really in good shape and I have caffeine and I sit down. It'll make my heart seriously ding 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 ding. It's not pleasant at all. Thank goodness I'm not in that great a shape right now. He's running. Okay. Partial derivative of this thing with respect to x. Come on, everybody. What is my my independent variable if I'm doing this right now?
X.
Which means I would have what?
Sine squared y.
Oh yeah. Minus, because that's a constant. And now if you're okay with that. For real. Yes, everybody? Now you find me this one. Notice how I'm switching my variable. What's my variable now? You're not excited. You should be excited. This is an exciting section. Cool. What's my variable now? So the derivative of this is, what do you need to take the derivative of this thing? Chain rule. Bring down the 2. Leave the inside function alone. Take the derivative of the inside function. Follow? 2 comes down, subtract 1 from it, you get 1. Leave the inside alone, derivative of the inside. You need to know chain rule. We do not have time to function around with this stuff. Okay, you got it. You got to have it. Now, the independent variable was, now it's y. It's y. So we get minus 2y sine x. That's it. That's it. No chain rule. No, well, technically it is, but no relevant chain rule, no product rule. Done. Head nod if you're okay with that one. Next up, we got, now start over. Start over. Now we have, let's take this derivative with respect to y. We're looking back up here. If you need to write it again, write it again. I don't care what you have to do. But we're starting back up here. Now y is your variable you start with. So we have, oh, that's a number. That's a constant. 2x sine y cosine y by the what rule? That's chain rule. Minus y squared, sorry. I lost track of my independent variable. What is it supposed to be? Plus 2y cosine x. That's not a variable for that situation. This is 2y cosine x. So finish, be okay with that one. Now let's keep on going. Let's do the second derivative. But now we switch gears and we drop down to x's. So we had y's, but now x needs to become my independent variable. Everyone, right now, do I need a product rule for this?
No.
That's 1 big 7. That's all it is. What's the derivative of 2x?
Sure.
Now this guy, this is now a constant. X is my only variable. It's going to take time to get used to. You don't get this after 1 hour or 2 hours. You get this after lots and lots and lots of practice. It's going to take you a lot of practice. You don't just magically go, oh yeah, I get it now. You're going to understand the concept, but you will still have to put your mind in the correct frame. That's why I always write this down. That's why I always think, what now is my independent variable? X is. So if x is my variable, that's a constant. 2x and then, derivative 2x is 2, the rest of the stuff. If x is now my variable, that's not. That means derivative of cosine x is negative sine x. Do you see how we got it? Unless you're sleeping, I guess. How can you sleep? I talk so loud. I don't know. Super boring. There should be something just slapping you right in the face right now. It's magic. Absolute magic. Do you see it? It's cool. It's why we did the second one. Just say, yeah, it's awesome. What happens? What happens? What happens? What's the same?
The derivative of x then y is the same as the derivative.
Did you catch it? This happens every single time, no matter what. I don't care what partials you have. We call these mixed partials. This is the next thing we'll start with when we come back from a break. Mixed partials are always equal. If you have partial x then y, partial y then x, I don't care. If you have x, y, z, then z, x, y, it doesn't matter. Every mixed partial is always equal. That's very impressive. I don't prove it, but that's a very impressive thing that we just found out. And now if you're okay with that one. That can save you some time. It's also a great way to check your work, isn't it? Also, if I say prove that they're equal, you have to show me both and prove that they literally prove that they are equal. Does that make sense? Let's take our break. When we come back, all we're going to do is pretty much practice some of the stuff. I'll give you the word problem, and we'll be done. All right, here we go. Yes, math time. Let's go back to this. What we learned in the last little bit was pretty darn cool. It says that this general statement, for any function that is continuous on a region, so basically if you don't have any discontinuities, that any mixed partial derivative, that's what the changing of those variables, like when you change with respect to x and then with respect to y, that's a mixed partial. Y then x, y then x then z, then whatever. Any mixed partial is equal. What that means is if I get a partial derivative of partial derivative of f with respect to x then y, that is going to be the same as the partial derivative of f with respect to y then x. It will be the same. This would be the same as zxy, which would be the same as the x y then x then z, but it's not the same as x then y then x. As long as you have the same letters, any mixed partial derivative will be equal. That's pretty cool. So, x, z, y, cool. How about z then x and y? No problem. Y then x and z, as long as you have the same letters, you're good to go. Any permutation of that, you're absolutely fine. Any mixed partial is going to be equal. As long as you run a continuous on a region, every polynomial is, so we're good as far as that goes. If your letters don't match up, that's when we have an issue. And now if you're okay with that one. I'm going to give you about a minute or so. It looks harder than it is. I want you to find me these 4 mixed partials. At this point, you should know what that means. Find the partial of f with respect to, which one would you do first? And then? And then? Okay, do them. Do all 4 of them. I'm going to put the first one up about, one of them up about every, 20 seconds or so. Give you time to do them on your own. Go ahead and start now. When you get more practice at this, it'll be easier for you to switch your head into what my independent variable is. But right now, just take your time. There's no reason to just fly through these. Take your time and really think, what is my independent variable right now? What am I actually doing? So here it was x. That's my variable. These are not 2xy cubed. You understand why this all went to 0 for this partial derivative? Hello, yes, no?
Yes.
Now from here, we switch gears. We go, let's do the partial derivative with respect to y of this thing. It says, of the thing that you just did, now take the partial derivative with respect to y. Y is our variable. We need to be getting 6xy squared. Did you make it that far? Okay, keep going. Now it says, of this thing that you just found, now consider z to be your variable. What's the derivative of this thing with respect to z?
0.
Gone. Crazy. Show of hands if you got that. Good for you guys. Start over. Derivative of f with respect to y says y is our variable, 3x squared y squared minus 2y z cubed. With me, yes, no?
Yes.
Now it says, from where you just were, z z is now your variable. This, gone. This, negative 6y z squared. Did you make it that far? Good for you. And now it says, from where you just were, now x is your variable. Come on, everybody. What's the derivative of this thing with respect to x?
0.
They're already the same. That's kind of cool. Okay, start over. Derivative of the function with respect to z. Let's see about that one. With respect to z, we have, no z's, gone. Z here says negative 3y squared z squared. And now if you're okay with that one. We keep on going with that, we go, okay, now z then a y. So from where you were, the derivative of z, now change your variable. Our variable is now y. We get negative 6y z squared. Did you make it that far? Please look at the board here real quick so I can make a little comment. Did you notice how this and this turned out to be the same?
Yes.
Every mixed partial has to work. And now we go, okay, partial z, then y, then x. Says look back where you were. Now x is your variable, there ain't none, so derivative is 0. With me on that one. Is this going to have the same result as these?
No.
No. So when we look at it, we go, okay, well, derivative of x, you know what, I already did that. Derivative of xy, I actually already did that. Derivative of x, then y, then x. So partial derivative of x first, then with y, then with x again says, oh, wait, I still have an x. That's 6y squared. It's not the same. So as long as all your letters are the same, your mixed partials turn out equal. As soon as we start messing up with that, then they don't. Show of hands for real if you feel all right with this idea. Okay. Tell you what, I got 2 hard problems. We're going to talk about this first one. I'm going to do the first half, you're going to do the second half, and then we have a word problem. We are done. I mean, I'd be remiss if I didn't do derivatives of inverse trig functions. I mean, come on. You got to have those somewhere in the arsenal of fun. Some of you are thinking right now, Leonard, shove it up your arsenal. All right, so anyway, just a fun little joke about, I don't want to talk about it. Let's find all second partial derivatives. So h sub xx, h sub xy, h sub yy, h sub yx. All second partials. I want you to follow the first. I'm going to do all of them for you. I want to show you exactly what I want, and then I want you to do the other ones on your own. Does that make sense? So let's try this. How we start this off, I want the partial derivative of h with respect to x. This would be chain rule, but x is my variable, y is not. The derivative of tan inverse, if you remember it, it's 1 over 1 plus inside stuff squared times the derivative of inside stuff. That's chain rule, but x is my variable. It's negative y over x squared. If I want to make it a little nicer, I'd hold that x squared to the denominator. Perfectly legal. Take that numerator, take this denominator, and I would distribute it. That right there is the first partial derivative of h with respect to x. Now, let's go again. Let's take another partial derivative with respect to x. Ladies and gentlemen, I want to know, firstly, are you okay with the calculus? Calculus is done here. Do you guys see where we got that? If x is our variable, we have x negative 1, bring the negative 1 down, y is a constant, x is negative 2, bring it back down, becomes a fraction. You follow? Also, I want to give you some advice. For things that have constants over variables, don't use quotient rule. That's too hard. Maybe think of this as negative y x squared plus y squared to the negative 1. You can also consider this to be that. I would certainly do that if I'm doing a second partial with respect to x. So from here, x is my variable still. I've got positive y, x squared plus y squared to the negative 2. But then by the chain rule, derivative of that crap with respect to x gives me 2x. Do you see where that comes from? You sure? Do you see why we don't have a quotient rule, why we don't have a product rule? Left side guys, are we okay with that? Huh? Yeah, okay, that's fine. This is this, right? With respect to x, that's a constant. This is not. That's a variable. Bring down the negative 1, positive y. chain rule says -2, derivative of the inside with respect to x, again, that's where we're getting that 2x. And I'm going to clean it up a little bit. We go, okay, this is 2xy all over x squared plus y squared squared. So this is our first, this is the partial derivative of h with respect to x 2 times in a row. Are you guys clear on that one? All right. Now, I also want to do x then y. X then y. Which one would I use? It doesn't matter. But the point of doing this, I have to start from one of these things, and then I gotta switch my variable. Are you with me? Having fun yet? I gotta switch my variable. If I do this, do I need quotient rule?
Yeah. Yes.
If y is my variable, okay, let me start again. I'm losing some of you. I did x already, correct? It's one of these two choices. Now I want y. Y becomes my variable. Which one would you use? It doesn't matter. But what I need you to see is quotient rule for this, if you choose that. Product rule for this, if you choose that. Either one. I don't care. I would choose quotient rule. I'm going to do that right now. So low d high minus high d low square the bottom. There you go. If I've done my algebra right, that's what we should have. Can you follow it? Now I'm going to ask you a different question. Can you do it?
Yes.
Can you try?
Yes.
Okay. Would you right now? I'm going to give you about 2 minutes just to at least get the first couple steps down. I want you to do that one right now. Let's take a minute. Just do that one. At least the setup of that one. Go for it. If I do that, is my first part here, is the chain rule involving tan inverse, is that going to change at all?
No.
Is the chain rule itself going to change at all if I just have y over x and y is my variable now? Am I going to have the negative y over x squared or just 1 over x? What am I going to have? Because y is that constant, or sorry, because y is my variable, x is my constant. I get 1 over x. That's it. Okay, well, what to do? Oh, what did I do?
Distribute this round or y over
Yeah, you
x.
could. It's not a great way to do it. We could do that. Honestly, you know what I probably would do? I'd probably pull this 1 over x up here, like that. And then I'd multiply by the LCD everywhere. I'd multiply by x squared, both numerator and denominator. So I'd pull this up and multiply by x squared over x squared. And I'd let this distribute. That would give us x over x squared plus y squared. That's probably the better choice. Clear the denominator. Clear the complex fraction. Clear the denominator. That's my number one. Now, I want you to work on the next one. I'm not going to tell you what, I'm going to cheat, okay? I'm not going to be doing that one. You tell me right now why I'm not going to be doing that one. Why not?
It's right there. It's already.
If you don't get that thing out of doing that, you know you're making mistakes, okay? I guarantee that that is going to be exactly the same. But you would do it to prove it. If I said, prove they're equal, you'd have to show it. You don't just go, because you said so, Leonard. And you're never wrong. I'm wrong sometimes. I'm not wrong about this. But you'd have to prove it by doing it. Does that make sense to you? So I'm not going to do this, but I know that I would have to show, to prove it on my test, prove my homework, whatever, that this is going to equal this. Any mixed partial, any mixed partials are equal. So, what I want you to do is find this one. What's the better choice for doing that? This format, left, or that format, right? Which one would you do? Let me ask this question. What's my variable still if I'm doing this? What's my variable? Would I want that one? Because I don't want to think quotient rule. If I don't have to use quotient rule, do you guys see that I don't need quotient rule? X is not my variable, man. It's a constant. This right there is the only variable. I use that one. So this derivative is bring down the power, negative x. Leave the inside stuff alone, negative 2. Times the derivative of the inside with respect to y is 2y. And we get this is negative 2xy over x squared plus y squared to the second. I'm going to erase this for a reason. I'd like a show of hands if you feel okay with this so far. Now I want to make a statement about something that some of you people, if you're an engineer, you're going to see this at some point. I want you to check this out. I want you to look at the second derivative with respect to x and x, so h sub xx, and I want you to look at h sub yy. Do they look similar? What's the only difference? That doesn't happen all the time. That's very special. That's called a Laplace equation. When you have, and verify that this would be the case, if I added them together, what would I get? If I add this plus that, I will get 0 because they're exactly the same thing with different signs. Whenever that happens, when h sub xx equals h sub yy equals 0, that's called a Laplace equation if h satisfies this. So this original thing is a Laplace equation. If the second derivative with respect to x, both times, equals the second derivative with respect to y, both times, but they're opposite signs. So that equation right there is considered to be a Laplace equation. What it's used for, it's used in a lot of harmonic functions. Examples would be like heat conduction, fluid flow. Laplace equations happen a lot. So this signifies that h, what we have, is a Laplace equation. Now, last one. I think this one's kind of fun. It's kind of weird. It's a weird example, but weird examples are kind of fun examples. The surface area of a, wait for it, the surface area of a blank in meters squared per kilogram, notice that that's going to give a surface area, an area of something, is given by the following equation. Surface area equals some constant times weight to this power times height to that power, where weight's given in kilograms and height's given in centimeters. Isn't that creepy? Who thinks of this stuff? Who thinks, how much skin do you have? Isn't that weird? Like, oh, well, I guess if you're trying to cover someone in paint, oh, I don't want to think down that road. That's just
Put solution on the skin.
That's my first thought was, how much skin do you have? That's nuts. Okay, but that's what this surface area question is asking. Or we could think about it maybe a little more reasonable. How much of your body? I don't want to think about exposing bodies in here either. Okay, so. Anyway, someone came up with this stuff, and I thought it was pretty cool. So we're going to talk about find the surface area of the surface area of a human in meters squared per kilogram is approximated by that. I don't know who does these things, who models this stuff, but here it is. This is the function of someone did a lot of empirical evidence, modeled it with some programming, and we got this function. Here's what we're going to ask: what makes your skin stretch faster? A change in height or a change in weight? That's interesting. We're going to answer that question with calculus. Now, it's going to have to be at a certain height and weight, because someone who's really tall and gains weight, or someone's really short and gains weight, someone's really fat and gains height, and someone who's really fat and skinny gains height, their surface area, their skin changes differently. So we're going to find this at a certain point. So find which increases surface area faster for a person who weighs 70 kilograms and has a height of 180 centimeters. So what grows skin faster? Stretches skin faster, I guess. For a person weighing 70 kilograms with a height of 180 centimeters. Weight or height? Well, now let's put this whole freaking idea together, okay? The whole idea is, if we restrict, listen, how many variables you got? How many variables do you got? Come on, how many? Two. So that in 3D, surface area would literally be a surface. It's another reason why I did. I thought it was pretty cool. Little juxtaposition there. It's a surface. If I restrict the movement along that surface to just an axis of width or just an axis of height, I'm going to be able to tell what's increasing faster, what the slope is doing, what's going to change for this person, their skin size greater, a change in height or a change in weight, when they're at that moment in time, that moment of height and weight. Well, if we restrict that motion along W, that means we're treating h as a constant. That means we find a partial derivative with respect to weight, find a partial derivative with respect to height. It's restricting that motion. It's holding the other one constant. So if we find partial s, partial weight, and partial s, partial height, well, these are just numbers. You can do the same exact thing. Height would be held constant, so I'd multiply that down. I think I've done it for you. So this would be 0, well, I'll just do it this way. 7184, so you can see where it comes from. We'd bring down the 0.425, you'd subtract 1 from it. Real life doesn't have pretty numbers. That right there represents how surface area is changing. You know this, derivative is a rate of change. Slope is a rate of change. How surface area changes, but only with respect to weight. So someone whose height stays constant and we let their weight change, what's happening to the surface area? That's what that's talking about. Should we understand that concept? The other one goes, okay, well, we have basically the same thing. If we hold weight to be constant and we have height as a thing that's growing. So constant weight, you just grow taller. some basic derivatives, but it's pretty cool. If we do this, if we plug in, so at 70 kilograms and 180 centimeters, here's what we get. I've done the math for you. This ends up being, but now could you do it? Could you do that partial derivative with respect to weight?
Yeah.
Could you do it? Bring down the power, subtract 1 from it, leave h alone. Bring down the power, subtract 1. I messed up. Bring down the power, I'm glad I did that. Bring down the power, subtract 1 from it, leave the w alone. That's going to give you these two, the way these two variables interact with our surface area, our skin, our amount of skin, surface area of skin. Here's what happens. Could you plug in 70 and 180? 70 and 180. Of course you could. If you do that, here's what we get. Now, I want you to interpret what this means. All right? Don't just be able to do the math. You can all do partial derivatives. It's bringing down a number and subtracting. It's easy. You can all plug numbers in, but now let's interpret. What this says is surface area is changing with respect to weight for this particular guy. Okay, he's 70 kilograms. He's 180 centimeters tall. For this particular guy, at a rate of 0.011 meters squared per kilogram. That means his skin is growing at that rate at that instant of time. A little bit fatter, a little bit taller, he's going to change differently. But right then, that's how weight is affecting surface area. Does that make sense? It's restricted to the weight. Now, height says if I hold the weight constant, then we get 0.0076 meters squared per kilogram. Which one's bigger? What that says is a change in weight for this particular person, a change in weight will affect their surface area more drastically than a change in height will for this one guy. Does that make sense to you? It's interesting. That's what's happening here. We can do the same thing for other stuff. For instance, a lot of times in business, I was a business major for a while. You have profit curves that have been modeled on labor and capital, the two things you need to do stuff. You need to have material and people to work with material. If we can hold constant labor or hold constant capital, we can figure out which one's increasing our profit more. Hold it constant. Say which one's going to grow. Should I put more capital or should I put more labor? It'll tell you. Because at that moment in time, it'll tell you which one to increase. And that's simplified, but that's the idea. The biggest thing I can tell you right now, before you go, can you please just remember that you are holding all but one variable constant? That limits the amount of times you have to do the product rule, but be careful on doing it. Sometimes you need it. Be careful on that. Be careful on the chain rule. Just be careful, mathematicians. I can't go over every example, but I hope that the ones I did were very illustrative for you, illustrated the concept well. Do you feel like you understand the concept fairly well at this point? It's going to take practice, get it down, and we're done with our section.